Hello everyone, I'm Mahmoud Yehia from University of Victoria. Today I give my presentation on the GMMT Revocable Group Merkle multi-tree signatures scheme. Here are the outline of the presentation. I'll start by an introduction. Then I give the description for the GMMT hash-based group signature scheme, followed by its security analysis, then the dynamic GMMT group signatures schemes. After that, the GMMT comparison with the group Merkle and dynamic group Merkle hash-based group signature scheme. At the end, I provide the conclusion of this work. Group signature schemes is a signature scheme wherein members share one public key, and any member is allowed to sign anonymously on behalf of the whole group. Group signatures scheme designates a group manager that is responsible for setup phase, revealing the signer's identity, and revoking the memberships of the group members when required. There are two security notions should be achieved by any group signatures scheme. The first one is the anonymity, which means that only the group manager can reveal the signer's identity. The second one is the traceability, which means that no one, including the group manager, can generate a valid signature, which cannot be opened or traced back to a group member. In 2018, the group Merkle scheme was proposed as the first post-quantum stateful hash-based group signatures scheme. It was stated that multi-tree approaches are not applicable, thus limiting the maximum number of supported signatures to 2 to the power 20. As a solution in 2019, dynamic group Merkle was proposed as a dynamic and revocable group Merkle-based group signatures scheme. It utilizes a computationally expensive packetable encryption for revocation, and it requires interaction between verifiers and the group manager for signature verification, which restricts its application for which restricts its use for certain number of applications. In addition, the group manager needs high storage requirement to be able to reveal the signer's identity. Accordingly, we propose the GMMT that solves the limitations that we mentioned previously in the of the group Merkle and the dynamic group Merkle. The GMMT is a hybrid construction of the group Merkle and a single signer multi-tree construction, where it encompasses several group Merkle trees denoted by cluster at layer 0 and one stateful hash-based signatures schemes from layer 1 up to layer d-1. And the top layer tree root is the group public key. Each group Merkle tree at layer 0 here, which is referred by cluster, contains a subset of one-time signing keys from all group members, while the multi-tree stateful hash-based signatures schemes is used by the group manager to sign the cluster root. This construction allows the cluster tree to be constructed adaptively as the signing leaves are used up. This allows the group manager to manage the leaf assignment for all group members in a clustered manner. The scheme enables a practical setup phase with less storage requirement for each group member compared to the group Merkle schemes, because not all the signing leaves for each group member have to be assigned up front, and a member can reuse the storage that was allocated for the previous use. Here for the key generation algorithm, the group manager samples randomly the secret key.enc, which used to reveal the signer's identity, and the secret key.seed, which is the secret key for each stateful hash-based signatures scheme. And the upper three-layer root is the group public key. Also, each group member generates their secret key SKI, which is used to generate the secret keys of their one-time signing keys at each cluster. Here we provide the signing leaves assignment and the cluster generation, that it has three phases. The first one is the label assignment, in which the group manager sets the maximum number of leaves that can be assigned to a member for the whole life of the scheme, denoted by BUmax, and then dedicates to each member a sequence of number corresponding to their identity. For all members from member I greater than or equal 1 and less than or equal to n-1. And for each group member, the group manager stores only the last assigned label in their dedicated range, in what we called user list here. This allows the group manager to store only one value per member corresponding to their identity. For the second phase, it's signing key generation, in which each group member generates B one-time signing public key from BK0 up to BK P-1 using their secret keys. And each one sends this public key to the group manager. Then the group manager performs the shuffling and clustering for the received public keys from all group members. And this is done by first make label assignment for each cluster, that the received public keys from each group member are labeled in the designated range. From the label B0 up to the label PB-1. Then these labels are encrypted using an encryption algorithm utilizing the group manager secret key.enc. And the label itself. So the label are encrypted. After that, the leaf are generated by hashing the concatenation of the public key and the corresponding encrypted label. Then these leaves are permuted using sort algorithm, which store the whole group members in ascending order with respect to the encrypted labels, EP. After that, the group manager builds the cluster tree and signs the tree root by its key, then distribute these values to all group members. For the signing algorithm, it takes the message M and the secret keys for the signing member, and it produces a signature that contains the index, which is the signing leaf index within the whole construction, and sigma auto one-time signing scheme and 0, which is the signature in the cluster by a group member on the message. Then the corresponding encrypted label and the authentication path auth0, which is colored in gray here in cluster 0, and the signature generated by the group manager for the cluster root. Here for the verification algorithm, the algorithm first check if the encrypted label exists in the revocation list or not. If it exists, means that the signature is revoked. Otherwise, the algorithm continue the following procedures for the verification. So it computes the one-time signing scheme verification on the message using the signature OTS at layer 0 or the cluster to produce a public key. And the calculated public key is hashed with the encrypted label received in the signature to get the leaf. And the calculated leaf with the auth 0 in the signature are used by root calculation algorithm to calculate the cluster root. Then the cluster root with the signatures generated by the group manager using the root calculation algorithm are used to get the upper layer group public key. And it's then it's compared with the group public key. If they are equal, then this is a valid signature. Otherwise, the signature is invalid. For the revocation algorithm, the group manager retrieves the last assigned label LA for the members that is wants to be revoked. Then the group manager generate all the encrypted label assigned for the revoked member and add this value to the revocation list, then perform the sorting to update the revocation list. And for opening algorithm, the group manager performs the decryption for the encrypted label in the signature utilizing the group manager secret key.enc to get the label B, then perform the flooring for B over BU max, where BU max is the maximum number of signatures that can supported by a group member in the whole life of the scheme to get the identity I for the signer. We provide the security analysis for the GMMT regarding to the standard security notions for group signatures scheme. We proved that the GMMT achieves correctness, where for an honest signer with a secret key SKI, the probability of verifying a signature that is generated by an honest group member to be equal 0 is negligible. Then we proved that the GMMT achieves anonymity and also it achieves the full traceability. Also, we proved that the GMMT maintains the anonymity of revoked members and linkability of their signatures. For dynamic GMMT, we can say that the GMMT can be adapted to allow adding new members at each cluster generation. And in this case, the number of leaves assigned for each group member decreases because the cluster height is fixed and the number of group members increased. A drawback of dynamic group Merkle multi-tree is that the anonymity game cannot be played on all clusters. That if the two challenging identity are for newly joined member and an older member, then the anonymity game must be played on the cluster which contains signing leaves for both members. In this case, the dynamic GMMT achieves anonymity. And if the anonymity game is played on the cluster that contains only the older group member, then the dynamic GMMT achieves linkable anonymity of revoked signatures. Here we provide the comparison between GMMT and group Merkle and dynamic group Merkle. For the comparison with group Merkle, here our scheme GMMT is a multi-tree construction, while it's only one tree construction in GM. Thus, our scheme can sign up to 2 to the power 64 messages, while it's restricted to 2 to the power 20 in the group Merkle scheme. And because of the multi-tree construction, our scheme signature size is larger than the one in the group Merkle. And for the group member storage requirement, the design in our scheme achieves that the group member will store will require a memory a storage that is less than the one used in the group Merkle by B signature element, plus the signature that is used by the group manager to sign the cluster root. And for reasonable parameters, our scheme achieve 5.6% storage less than the one used in the group Merkle scheme. And for the comparison with the dynamic group Merkle schemes, DGM doesn't achieve executability, where the group manager generate the one-time signing schemes keys for the group members, while our schemes GMMT achieve executability, where the group members themselves generate their one-time signing scheme keys. For DGM, it's required that the verifier to interact with the group manager for the verification, and this limits their use for certain applications, while this is not the case in our scheme GMMT, where it's not required that the verifier to interact with the group manager. For the revocation efficiency, DGM achieve linear complexity with respect to the revoked signatures, while our scheme GMMT achieve logarithmic complexity with respect to the revoked signatures. And for the group manager storage requirement, the DGM group manager needs to store the all index assigned for all members. Thus, for a reasonable parameters, the group manager in DGM require 10 to the power 8.7 terabyte. But this is not the case for our scheme, where the group manager need to store only one value per member. Accordingly, the storage for the same parameter will be 1 megabyte. And for the signature size, because our scheme is a multi-tree construction, so the signature size in GMMT is larger than the one in DGM. For the conclusion of our work, we propose that the GMMT are revocable post-quantum hash-based group signature schemes. The GMMT is a multi-tree construction that allow up to the power 64 signature that solves the problem of the group Merkle of being one tree construction. Thus, limits the number of signatures to 2 to the power 20. The GMMT solves the following drawbacks of dynamic group Merkle signing scheme. The verification procedures don't require interaction with the group manager. The required storage for the group manager is linear in the number of the members, while it was linear in the number of signatures in the case of the DGM. Our scheme reduces the computational complexity of checking revocation. Also, we provided an alternative revocation mechanism that is equivalent to the traditional revocation by key to solve the problem of large revocation list for some applications that don't require anonymity of the revoked members. Thank you for watching my presentation. Thank you.